We know that E naught value is a measure of sublimation enthalpy, ionization enthalpy, hydration enthalpy. Now, this is the E naught value for the element M changes to M2 plus, whether it will release electrons in not. This is M2 plus. Can you say this is 2 plus written? M changes to M2 plus. Its E naught value is here you know zinc value you know that is minus 0.76 that we are already going on. Copper you know that is 0.34 plus 0.34. Then what iron you know minus 0.44. These many values already you know. Other values are also written. You don't have to buy by this values, but the trend you should learn. You know that zinc releases 2 electrons, one zinc atom releases 2 electrons. Copper difficult, 2 electrons difficult. Plus 2, this is M2, M2 plus, general M2, M2 plus. Zinc releases with negative sign, the electrochemical series, we wrote zinc down, here zinc down and copper up, and we said zinc releases 2 electrons very easily. We know the value of zinc is minus 0.76, copper plus 0.34, copper will not release those 2 electrons easily, it has got a positive, it has got a positive electron value. Now, if this is the condition, you know this iron can also release 2 electrons, but zinc releases very easily. Zinc releases very easily. Releases very easily. You know the reason why? Because after the release of 2 electrons, zinc will attain that D10 stability. D10 stability. So zinc releases very easily. So that is shown by its negative sign. High negative sign minus 0.76 compared to this copper. If that is the condition, will titanium release electron very easily? Minus 1 point, that is minus 0.76. Will titanium release scandium? I haven't written because scandium plus 2 does not remain plus 2. Even if it is a plus 2, it will change to plus 3 to attain the nearest Frobenius configuration. Scandium will not show plus 2. So I am not writing scandium here because here plus 2. From M to plus 2. Neutral to plus 2. Scandium directly changes to plus 3. So, this value is greater than or easily releasing zinc, that means titanium will release very much easily as compared to zinc. Titanium. Why it is so? Bigger size. Bigger size. The size, you know that the size this much, then this much, then this much, then this much, then smaller, smaller, and when FECO almost same size the reason we said. So if the size is bigger, that means those 2 electrons are far away from the nucleus. So titanium can release those 2 electrons very easily. What about vanadium? Minus 1.16. Minus 1.18. Because size is little smaller. Size is little smaller. So compared to titanium, vanadium will not release that much easily. What about chromium? Chromium plus 2. I'm talking about plus 2, not plus 1. Remember, it will be high minus, but this is plus 2. So size reduced. But when it comes to manganese, This is 0.9 minus 0.9. We expect some minus 6 minus 0.6 minus 0.6. We expect but the value is high minus. The reason is what? After the release of those two electrons, manganese attains that half-full stability. So, this is an exceptional case. This is not in the trend. This value is not in the trend. We expected some minus 0.6 or minus 0.7 like that. Right? So, the reason we have said after this. Now, if this is minus 0.6, of course this will be minus 0.4, that is in the trend only. Then minus 0.2, that is in the trend only. Then we expect some minus 0.4, minus 0.2, so some 0 here plus 1 like that, 0 here plus 1 like that, but here it is again 5 minus. So this is an exceptional case. This is an exceptional case. The reason is that not because of that D10, D5 stability, its hydration enthalpy is very high. By heart, nickel is, the hydration enthalpy of nickel is very high, which accounts for that. This is in water. Value is in water. So, this hydration, sublimation enthalpy, ionization enthalpy, and hydration enthalpy. You can buy one nickel piece from the market. First, you have to sublime this thing. It's separate into gaseous atoms. Then take two electrons. Take two electrons ionization. That is it. In water, then hydration. Hydration level of nickel is very high. The sentence you have to buy heart. Hydration. Due to that, then nickel will be releasing those electrons. That is from M to M. Now Cu plus 3. Now you can say if this would have been plus 1, then plus 0.3 plus 0.1, then it would have been plus 0.3. Again, it is coming to a positive. Positive due to its high sublimation enthalpy or high enthalpy of atomization. Still, it is somewhat we can say the trend only, so we expect zinc to have high positive, maybe plus 0.5, but it is coming to minus 0.7. This is coming to somewhat here, somewhat here. That means the reason that is after the release of these that zinc attains D10 stability. Zinc attains D10 stability. So exceptional cases are that manganese, nickel, and zinc. Manganese, nickel, and zinc. Manganese, D5 half stability. Nickel, high hydration enthalpy, and zinc, D10 stability. Now coming to this, from M2 plus to M3 plus. From MC already M2 plus 1. Now from that one more electron, in which case you expect one more electron that will be done very easily. So I'm taking the values minus 0.37. Don't have to by heart this values. Minus 0.26. Then minus 0.41. And here, in the case we have to learn this thing on manganese. In the case of manganese, minus 0.41. In the case of manganese, it is plus 1.57. Plus 1.57. Not easy. Because already it is in the M2 plus means it's the D5 stability. You cannot touch one electron from there. That is not possible. So this plus means it is not possible. M2 from M2 plus. So you have to learn only this thing from here. That is from M2 plus to M3 plus 1.57 it is not that much feasible because you have to disturb that K5 stability. So these are the primary mean of matters. Now, one question you write, nickel 2 compounds are not like that. K2PtCl6 is a well-known compound. K2, K2PtCl6. K2PtCl6 is a well-known compound. But corresponding nickel salt is not known. Corresponding nickel salt, that is K2NiCl. Corresponding nickel salt is not known. What is the reason? So here, what is the oxidation state of Pt? What should have been the oxidation state in nickel there? Here, Pt, this is plus 2 and this is minus 2. This is minus 6. So this will be plus 4. Similarly, is the case. So Pt plus 4 and then nickel plus 4. Plus 4 means IE1 plus IE2 plus IE3 plus IE4. Shorten value we have received. Similarly, nickels plus IE1 plus IE2 plus IE3 plus IE4. This will be the ionization energy required here will be less. That will be more. That's why that is not feasible. So you have to write like this, work like this only, IE1 plus IE2 plus IE3 plus IE4. IE4 of platinum is less as compared to this value of nickel. So this is not easily, that is not found, that is the reason. But if it is plus 2, Pt plus 2 and Na plus 2, then this is well-known compound, NiSO4, NiO, NiCl2, NiCl2, like that. That plus 2 is stable for nickel, plus 4 is stable for platinum. Here what you have to write, IE1 plus IE2 of nickel is less as compared to IE1 plus IE2 of platinum. Right? So the same question you write in this format also. Nickel 2 compounds. Nickel 2 compounds are more stable than Pt2. Nickel 2 compounds are more stable than P2. Why? Whereas Pt4 compounds are more stable than nickel 4. Pt4 compounds are more stable than N4. So you have to write in terms of ionization energy. How much energy and then how much energy we have to give? How much energy we have to give? If we have to give less amount of enthalpy, less amount of energy, means that is easily possible. That is possible easily. So here, nickel plus 4, Pt plus 4. Here, nickel plus 2, Pt plus 2. They say Pt plus 4, that is easily formed. But nickel plus 4, the compound is not known. See, K2PtCl6 is a well-known compound, but corresponding nickel is not known. Not known means it is not there, not existing, not at all stable. Stable, it will exist. So we have to write IE1 plus IE2 plus IE3 plus IE4. Heating calculate. You have to calculate simply right values according to the question. Similarly, Nicholas IE1 plus IE2 plus IE3 plus IE4 you add and find out. This will be less. Heatings will be less. Nickels will be more. Now coming to ET2 plus NI2 plus. So IE1 plus I2. Calculate IE1 plus IE2 for both. You will see nickels will be less, PT will be higher. So that about ionization enthalpy. Ionization enthalpy. Next, we are moving to the properties of these D block elements. What are the properties exhibited by D block elements? Last year we know. What are the characteristics of D block elements? They show variable valency, they act as catalyst, then they are paramagnetic in nature, variable valency, they are metals, uh, they exhibit color. Last year we learned PV, that paracolor. PV meant paracolor, variable valency, they are metals, they are paramagnetic, they exhibit color, they act as catalyst. These are the characteristics of D block elements. So let's see how they are actually. First thing we just learned, they show variable values, or they can exist as, they can act as catalysts. Let's see how they can act as catalysts. Due to the variable valency only, they can act as a catalyst. For example, iron Fe plus 2, Fe plus 3. Fe plus 2, Fe plus Fe can exhibit variable values. Now I'm giving one, I'm going to write one equation. How does Fe can act as catalyst? 2I minus plus S2OH 2 minus. It was actually Na plus 2OH. Gives I2 plus 2SO4 इसका कोई सा भी ऑप्शन वाला इसका को फाइनल विल बी SO4. Final will be SO4. This reaction we are using, for this reaction we are using iron as the catalyst. How does iron act as a catalyst? First Fe2 plus. So Fe2 plus will be reacting with this first one, that is 2I minus. This is the equation 2I minus. And what will happen? This Fe2 plus will change to Fe3 plus. That is Fe3 plus, that is catalyst only, plus what? I. Now, this Fe2 plus form will react to this H2OH. I'm writing that Fe3 plus will react with H2OH2 minus. Now what will happen? Fe2 plus will change to Fe3 plus will change to Fe3 plus, and its final product will be a thing, that is 2SO4 2. This is the reaction. So Fe2 plus will be reacting with 1, and this product is I2, this product is. Then the Fe2 plus form will react with this one and form Fe2 plus and plus next product. That means what we put in there that got regenerated. As we learn catalyst, what we are putting, that will be regenerated. Nothing is going to, finally nothing is going to happen to this catalyst. What catalyst you have added, that will be coming back. So you can ask, why is this transition element or D block element acting as catalyst? Because they can show variable balancing. Not only that, that can give the solids. They are solids, so solids can give the surface area. Surface area. So it will. This catalyst will reduce the activation energy. Activation energy means you know that progress of reaction or reaction point. Reaction point. Where you can write progress of reaction. This is potential energy. Last year you learned like this one curve. If I can, this is the reactance energy. This is the products energy. The products energy. Amount of energy given to the reactant is called activation energy. When catalyst is used, then catalyst will take that through a lower path. That means activation energy you have to supply is only this much. This activation energy without catalyst. Without catalyst. This activation energy with catalyst. You have to supply always energy. Means you have to supply only the sum of energy. When a catalyst is so reactants react together to form products. So that is another use of this catalyst. Main is due to why it is acting as a catalyst, that is due to the variable valency that they can show. Variable valency. So catalysts can act as transition elements can act as catalyst account. This is due to the variable valency. This is due to the variable valency, and you show this reaction. Plus, you can write what all things they provide a surface area. They provide the surface area so that these reactants can be absorbed. That is diffusion of these reactants on the surface of the catalyst, then adsorption of these reactants on the surface of the catalyst, a chemical reaction takes place on the surface of the catalyst, then what dissorption of the products on the surface of the catalyst, we learned that in chapter 5, and diffusion of the products on the surface of the catalyst. So we can simply say for these 5 steps, we can simply say catalyst provide the surface area. That's all. Activation energy is lowered. So these are the 3 reasons why the transition elements can act as catalyst. First and foremost, variable balancing. If you are writing only variable balancing, you will be getting full mark. To support your answer, you can say that it provides surface area, then it reduces this activation. Next, colored compounds. Why do they give colored compounds? Transition elements. Transition elements or D block elements that mainly depends upon the d orbitals. D orbitals. D orbitals we know like this. 3D X1, 3D Y Z, 3D YZ, then 3D XZ, 3D XZ, then 3D X square minus Y square. Then that is on the axis. That is on the axis. Then 3D Z square, you consider all of them, you will see like a flower all around. 3D Z square. donut shaped, 3D Z square. So these all you consider together means in all directions. Some are in between the axis, some are lying on the axis. 3D x square minus y square is lying on the axis. This is also on the axis. So this 1 and this 2. These two are lying on the axis and others are in between the axis. X, Y in between. X, Y in between. But here this is on the axis. Now, when species with electron pair comes to make bond with the empty d orbitals of transition. What I said? There are d orbitals. We can also these d orbitals undergo hybridization and make orbitals of equivalent energy and identical shape. To those empty orbitals from outside, if species with pairs of electrons come to make bond with by filling these empty orbitals, those species are called ligands, and we will study in next chapter. Ligands. Ligands. They are coming from outside. So when they come from outside, suppose 6 are coming from outside. One is from here, one from here, from top, from bottom, from that side, from this side. Just like an octahedral wave, if it comes. Then, if they are coming along this axis, that is x-axis, y-axis, z-axis. When these ligands are coming, they are approaching this D block metal atom. Then the orbitals which are lying on the axis, orbitals which are lying on the axis will be under repulsion. So their energies will be high. Accordingly, energy is concerned. Accordingly, the energies of orbitals which are lying in between, their energy will be lower. So these degenerate orbitals now, their degeneracy is lost. Degeneracy is lost. Degenerate orbitals means we were telling all these five orbitals are having same energy. All these five orbitals are having same energy. Now the degeneracy is lost, means 2 are having under repulsion, they are having higher energy, and 3 are having lower energy. Here we call it as EG set. This is P2G. We will continue the next class. Thank you.